सब्सक्राइब कीजिए ईएसए क्लासेस चैनल को और बेल आइकन दबाइए हमारे लेटेस्ट वीडियो सबसे पहले देखने के लिए।
Kinetic theory of gases, second part. Absorption, reflection and transmission of heat. If Q is the incident radiant energy, then QA, QR and QT, these are absorbed energy, reflected energy and transmitted energy. Then coefficient of absorption. Coefficient of absorption is defined as a ratio of radiant energy absorbed to radiant energy incident in the same time. It is the radiant energy absorbed upon total energy incident. It is also called absorptivity or coefficient of absorption. Then coefficient of reflection. It is the reflected energy upon incident energy. It is also called reflectivity or coefficient of reflectance. Coefficient of transmission. It is energy transmitted upon energy incident. It is called transmittivity or coefficient of transmittance. Coefficient of absorption plus coefficient of reflection plus coefficient of transmission is equal to 1. Then athermalous substances means bad transmitter of heat. Athermalous substances means bad transmitter of heat. A plus R is equal to 1. T is almost 0. Coefficient of transmission is almost 0. Examples are water, wood, iron, lamp black and copper. Then diathermalous substances. They are good transmitter of heat. Examples NaCl, glass, quartz, H2, N2O2, rock salt, air, dry air. Then perfectly black body. Perfectly black body has coefficient of absorption 1. It absorbs all the energy incident on it. So reflection is 0, transmission is also 0. No body is perfectly black. Lamp black is nearly black body. It absorbs about 98% of the energy incident. Then fairy created black body. It is called fairy's black body. Its structure is like this. This is double-walled sphere. This is double-walled sphere. Outer surface of outer sphere is nickel polished. Volume between the two spheres is evacuated. Evacuation and nickel polish is done to avoid heat transfer from outside into the sphere. Heat transfer should not happen between outside and inside. Therefore, vacuum is provided as insulation and nickel polishing is done so that incident radiation should get reflected. Then here is conical projection to deviate the incoming rays. An inner surface has a lamp black on it. So entire structure is not black body. This opening is black body. So whatever amount of light, whatever amount of radiant energy is incident through this hole is totally absorbed. If radiations come like this, they get deviated. Here there is 98% absorption. Here 98% absorption of the remaining. Here 98% absorption of the remaining. So within 1, 2, 3, 4, 4 to 5 reflections, almost all the energy is absorbed. Spectrum of blackbody radiation in terms of lambda. On this axis we have E lambda. E lambda is derivative of energy radiated per unit area per unit time with respect to lambda. On this axis we have derivative of energy emitted per unit area per unit time with respect to lambda, and on x-axis we have lambda. These graphs give distribution of energy as per the lambda. So if we calculate area under this graph is drawn when body is at 1000 Kelvin. This graph is drawn when body is at 1000 Kelvin. So when body is at 1000 Kelvin, area under this graph for lambda 1 to lambda 2 gives energy radiated per unit area per unit time, energy radiated per unit area per unit time by that body at 1000 Kelvin through wavelengths from lambda 1 to lambda 2, through wavelengths from lambda 1 to lambda 2. So distribution of energy with respect to lambda is non-linear. As temperature increases, height of the graph increases, means total radiated energy also increases. As temperature of the body increases, peak shifts towards the left. Means as we increase temperature of the body, lambda max decreases. Wien gave the relation between lambda max and temperature. T temperature is in Kelvin, so lambda max is proportional to 1 upon temperature. Lambda max is equal to some constant into 1 upon T. This is Wien's constant. Wien's constant is 2.898 into 10 raised to minus 3 meter Kelvin. This is useful to calculate temperature of distant stars. Then emissive power. Emissive power is energy emitted per unit area per unit time. It is the energy emitted per unit area per unit time. It depends upon temperature of the body, nature of the body, and nature of the surrounding. Energy emitted by a perfectly black body is greater than energy emitted by other bodies. Good absorber is good emitter. And good reflector is not good emitter. Good reflector is never good emitter. Then emissivity. Coefficient of emission is defined as energy emitted by normal body upon energy emitted by black body. Emissive power of normal body upon emissive power of black body. Then absorptive power. Absorptive power is energy absorbed per unit area per unit time. Good absorber is good emitter. Then Kirchhoff's law of radiation. Kirchhoff's law of radiation is coefficient of absorption is equal to coefficient of emission. Coefficient of absorption is equal to coefficient of emission. Coefficient of emission is E upon EB, energy emitted by normal body per unit area per unit time, divided by energy emitted by black body per unit area per unit time. This we can write like this: E upon A is equal to EB. Then Stephen's law of radiation. Law is this: energy radiated per unit area per unit time by any body is proportional to temperature raised to 4. Energy radiated per unit area per unit time is proportional to T raised to 4. Temperature is in Kelvin. This law is useful for black body as well as for normal body. So for black body we can write EB is equal to sigma T raised to 4. Sigma is proportionality constant. And for ordinary body we can write E is equal to E sigma T raised to 4. Here E sigma are proportionality constant, is coefficient of emission. Then sigma is very simple to remember, 5, 6, 7, 8. 5, 6, 7, 8. 5.67 into 10 raised to minus 8. This is the energy emitted by black body by normal body. Energy loss per unit area per unit time by normal body. That is E sigma T raised to 4 minus T naught raised to 4. What is it? E sigma T raised to 4 minus T naught raised to 4. T is the what? Temperature of the body, and T naught is the temperature of the surrounding. Then object losses energy to the surrounding. This much energy is lost by object to the surrounding. Then Newton's law of cooling. Newton's law is this: rate of loss of heat is proportional to excess temperature over the surrounding. Rate of loss of heat is proportional to excess temperature over the surrounding, and excess should be small. So dq upon dt is proportional to theta minus theta naught. Theta, temperature of the body, theta naught, temperature of the surrounding, and k is the proportionality constant. We can write this in this form as well. Rate of cooling d theta upon dt. Rate of cooling d theta upon dt is proportional to theta minus theta naught. D theta upon dt is equal to some proportionality constant kt into theta minus theta naught. If we integrate this, equation becomes like this. Okay. If temperature of a body comes down from 60 to 42, temperature of a body comes down from 60 to 42 in 5 minutes, and temperature of the surrounding is 30 degree, then this equation we can apply like this: log of theta 2 is the final temperature minus theta naught is the temperature of the surrounding. Theta 1 is the initial temperature minus theta naught is the temperature of the surrounding, is equal to constant into time. Time is in minutes, so we can put it directly. As per the unit of time, unit of kt changes. This is how we can calculate kt, and this kt can be used in further calculations. Then limitations. Limitations of this law: theta minus theta naught, excess over the surrounding should be small, and this is not radiation law. This is not radiation law. This law considers convection, conduction, and radiation, all three. Then greenhouse effect. Greenhouse, without greenhouse effect, temperature of earth would have been minus 18 degree. Because of greenhouse effect, temperature of the earth has increased, and it has become good for the organisms. But in last 200 years, because of man-made pollution, amount of greenhouse gases in atmosphere is increasing. Because of that, temperature of the atmosphere of the earth is increasing beyond normal limit, and that is dangerous for the organisms on the earth. So by controlling pollution, we can control greenhouse effect. These gases produce greenhouse effect.